and for the Federal Universidade of the Goiás, speak about the vector method to prove quark axial current, and 2, quark meson mix and flavor symmetry breaking C quarks. Please, Fabio.
Working? Is it working? The microphone? No.
I think so.
Okay, okay. Thank you very much for the organization for this time to give this talk. I will talk about 2 different issues. This is product of my doubt when sending the abstract, so I decided to send the 2 works. I thought it could be interesting.
Microphone not working.
Microphone. Yeah. Now? Okay. So this work is based. This talk is based in these works I've been doing the last years, in the last few years, and I will talk. They are from 2 different approaches concerning rather effective models for QCD, mainly low energy QCD. And then this is the outline. I'll do some motivations and the context. Then I'll talk a little bit about a vector meso interaction with the constituent quark axial current, and show the relation to the pion axial coupling and its form factor. In fact, this, where's the point? Is there a point? Cima. Okay. In fact, this this coupling gives rise to a axial content of the vector mesons, and then I will switch this subject to the Nambu-Yonah-Lazinian model. That's a very well-known model for low energy QCD, and show different types of effect based on mixings between quark and mesons. And then I will show some consequences of these mixings that happen in the C-quark level. So this comes from an improved Nambu-Yonah-Lazinian model. So this issue is, this slide is just to, I have to give some motivation. This is very well known. Low energy QCD effective models are very good for global hadron properties. They usually take into account dynamical chiral symmetry breaking by means of the quark-antiquark condensate. And then somehow this quark-antiquark condensate is sort of manifestation. We can associate these condensates to these C quarks that may form a cloud around the valence quark inside a meson. And then usually people think that these models are nearly exhausted, they have nearly exhausted their resources. In spite of that, I think they are still good for some phenomenology and also as a test model for new scenarios, as I intend to show. And then it's based on a punctual interaction that may be identified to the inverse of gluon effective mass or to a square of a QCD cutoff. And it deals explicitly only with valence quarks to provide the hadron spectra. And then usually if you want to improve this model, you have to introduce new interactions, new free parameters to fit some observables. And then when you talk about the C quarks, it's natural to think, as I've been discussing in this conference, in this workshop, the different C quarks content of, for example, the nucleon. And then the strangeness content of the nucleon, it's quite well established. If you take some electromagnetic properties, can be of the order of 5%. And the charm content of the nucleon has been proposed some time ago. And lately, there was some evidence, 3 sigma level confidence for for a 1% contribution for the nucleon properties. So I apologize, I will not quote every work. They should be really associated, so I will quote some of them just to make presentation more compact. And then this is the result. In fact, I will show some mixings that give rise to the flavor breaking in the level of C quarks in the Nambu-Lalazinho model. So the second issue is about the vector mesons that may be used to probe axial current. Usually, you take pions or axial mesons to couple to the nucleon, to the axial charge. And we can, in the framework of the constituent quark model, that's quite a reliable model for the hadron spectra, these mesons could couple directly to these constituent quarks. And then, on the other hand, if we take high energy collisions, non-central collisions, vector mesons may be quite abundantly produced in non-central collisions. So I will take a framework that with which I've been working for some years already, for almost 10 years, that were with the aim of calculate meson couplings to constituent quark currents by taking into account the gluon dressing to these valence quarks. And then I will show some kind of non-leading coupling of the vector meson to the axial current. And then speculate if a photon then, by means of a sort of vector meson dominance, can probe also the axial current. So this is a starting point for the second issue. I will start with the second one. Let's consider this quark-anti-quark interaction mediated by a sort of non-perturbative gluon. This is a leading term of the QCD effective action, quark effective action. So we have quark currents interacting by means of a gluon propagator. This can be an input for this calculation. I will not calculate a gluon propagator. And I will consider that it's given by some other calculation. And then the usual logic is to manipulate these interactions by opening all the flavor and Dirac channels with Fierce transformations, and then we can introduce bilocal auxiliary fields that can give rise to local meson fields, and this should take into account the quark-anti-quark states that may emerge, all the combinations that can emerge from this sort of interaction. I will not present details. This is a result of this manipulation. So we are led to a quark determinant. There are some ambiguities in dealing with this quark determinant, depending on the symmetries we want to impose in this quantity. And then we can extract for example, here the pion coupling, the axial pion coupling to the constituent quark current. This is an axial meson coupling to the constituent quark current. Here are some vector couplings of the leading isotriplet vector and this isosinglet vector to the vector currents. In fact, all these quantities that we may associate to coupling constant, they appear as form factors. So we have this sort of calculations, this for a constituent quark current, and this for the coupling of a meson to this constituent quark current. Sometimes it appears some two meson coupling to this constituent quark current. And then usually we choose a point of these form factors to pick up to calculate a coupling constant. Usually there are these two possibilities. When calculating these form factors numerically by choosing a gluon propagator that inside here this form factor, usually I choose a point, a sort of renormalization condition for the axial coupling constant. Usually in the constituent quark model, it is given by 1. And all the others, coupling constants and form factor, they appear in this correct order of magnitude. So this is the picture, and we start with this quark determinant, then the gluon cloud dress the quark currents that give rise to dressed or eventually constituent quarks. And then by using the Goldstone theory, the pseudoscalar, light pseudoscalar, I mean the pseudoscalar mesons quark antiquark state, they give rise to a pion cloud, and then we have this sort of contributions for the constituent quark, the gluon cloud and the pion cloud. In the last part, I will talk about the effect of symmetry, flavor symmetry breaking in this constituent quark that will give rise to different C quark, let me say, cloud. So, but besides the usual couplings of light mesons to their currents that usually have the same quantum number, there are also unusual couplings here of the light vector meson with the axial quark current. So this is the stress tensor, the abelian part of the vector isotriplet vector meson tensor to the axial current, isotriplet axial current, by means of a Levi-Civita. So this constrains both the momenta of the quark and the direction of the momenta of the meson. Besides that, the polarization of the vector meson is also constrained. They are all transversal quantities. And then this sort of form factor, I'll show a little bit of it in the next slide. It depends on the, let me say, incoming quark or incoming antiquark, and on the incoming meson momentum Q. So besides I mean, by dealing with all channels of the flavor channels of the quark antiquark state, we also have axial, isosinglet, and isotriplet axial mesons, and then we have the chiral partners also to the vector mesons, but also the corresponding couplings or form factors of axial mesons coupling to the vector current. And then we can compare this Levi-Civita. It appears from a sort of anomalous trace of Dirac matrix. So sometimes I call this coupling anomalous, although it does not result from an anomaly strictly. And then we can compare this coupling constant or this form factor to the pion axial form factor, for example. And then we have, by calculated in the same method, in this one loop polarization way. And then we have this ratio of this vector coupling to the axial current, its ratio to the axial, pion axial form factor. And we find that this form factor is suppressed by the 4 times the constituent quark mass. So it should be small, but anyway, it should be present in the interactions of the vector meson. Usually the coupling constant, the zero momentum limit of this form factor could be taken as 1 or pion mass for the momentum of the pion. For the momentum of the quark, this is not clear. These quarks are confined. They are not even quasi-particle of the system. So there is a large arbitrarity on how to consider this quark moment strictly. And then we can also compare this form factor to the vector form factor, to the vector meson coupling to the vector current at a certain momentum scale of the order of 200 to 500 MeV. This goes to 10% of that value. So just speculating, then we can, if a photon comes close to the nucleon by means of the vector meson dominance and of this sort of mixing of vector and axial current, this photon could also be probing the axial current, although with a reduced strength. Besides that, I was looking at when I was doing the calculation, I had a paper by Witten in mind, and then I used the same method he used to assess the interactions that may appear from the axial anomaly. And then we just put this whole action term of this coupling of the vector meson to the axial current in a 5-dimensional closed surface. And then by Stokes' theorem, we find that this action term, this is an actual action term, it is quantized, it should be multiple, given by multiple integers of a constant. And then we have here the sum of all these channels of Lorentz indices that include the momentum directions and the vector meson polarization. I started doing some more calculations about that, but I did not yet find a real clear result. So this is a sum of several terms, and eventually it should be related to the spin content of the constituent quark, eventually by assembling 3 quarks of the nucleon, and gluons, of course, of the nucleon. And then here it's a way of disentangle these terms by which of the currents, but I will not go further in this subject. So at the same time, but here from the previous slide, there's this ratio between this vector coupling and the pion coupling. So if this coupling if this term is sort of quantized from a sort of spin rule that can extract from here, the axial pion coupling may also be subject to this quantization. But I don't have a proof because if you take higher order loops, there might have some difference in this ratio. This is a plot of this form factor. So this is the form factor VGA, and here is the vector meson momentum square in the space-like region. And then for different constituent quark masses and the different quark constituent quark momentum, the behavior is only given for very low energy so far. At higher energies, there should have further contributions from other processes. And also from this form factor, we can extract an axial quadratic, average quadratic radius for the rho and for the omega. They are very similar. This is the value of the quadratic average radius for the extracted from the same method I was calculating. That's in the range calculated by other people. And when you calculate the axial quadratic radius of the rho, this goes from 10% of the value of the standard value of that people usually calculate. And this is a plot of the dependence of this axial radius of the rho as function of the quark effective mass for 2 different gluon propagators here, effective gluon propagators. So now I'll move to the Nambu-Ion-Lagrangian, improved Nambu-Ion-Lagrangian. So this is the standard Lagrangian for the standard Nambu-Ion-Lagrangian. This coupling constant goes like 1 over gluon mass squared, 1 over ultraviolet cutoff squared, and then we have the constituent quark mass generated by the quark-antiquark condensate, and all the spectra, usually the spectra of the light mesons are very well reproduced with Nambu-Ion-Lagrangian, sometimes with further interactions. There is a big problem besides the scalar mesons that are a problem themselves because they are not usually described by quark-antiquark interactions. That's given by the eta puzzle, the mass of the eta prime to be described. Usually, you need to introduce a further interaction here of a higher order. That's called the Toth determinantal interaction induced by instantons. And then I will be back a little bit more on this subject, because in fact, what we found that those mixings, they give another explanation, another description for this, for the masses of the eta prime. Besides that, there is another mechanism that generates the same total interaction. That's this vacuum polarization for the next term here. It also produces an interaction similar of the same shape without taking into account instanton, just by considering one loop calculation. So this is the usual pseudo-scalar spectra, the set of Goldstone bosons plus the singlet and the octet that will give rise eventually to eta prime if further corrections appear. And then we can just by identifying here each generator of the group to each of the pseudo-scalar mesons, this will be helpful in the next slides. So I had two reasons to improve the Nambu-Lasinho. First of all, if you take the standard version, we have fixed coupling constant, one loop equations to describe their masses by means of the gap equation, and one loop equations to describe meson masses from a bound state equation, a bit-salpeter equation at the Born level. Besides that, if you take Kisu de Lagrangian, flavor symmetry appears only in the quark mass. But when you take an effective model, there's no reason for one of the effective model parameters of the effective model do not depend on the fundamental degrees of freedom. So why not the coupling constants themselves also depend on the flavor asymmetry of the QCD Lagrangian. This is the idea of Winder when he formulated that sort of theorem in 1979 that gave rise to the chiral perturbation theory. And then for that, instead of introducing further free parameters, I will calculate one loop corrections to the coupling constant by means of a background field or external field method. And then these are the diagrams we will have to calculate. It could be at the determinantal level. This is for the Nambu-Lasinho with the Nambu-Lasinho degrees of freedom. And this is for a more fundamental process where two gluons are exchanged. So the flavor structure of these two sorts of process are very similar. And the result is that they will generate corrections to the coupling constant that will be flavor dependent. So we will have coupling constant that depends on if of the effective mass, the gap equation will be different, and this GFF now takes into account all the flavors that are not F here, because these coupling constants, all of them depend on all the quark effective mass because of flavor breaking. And then we have to solve self-consistently the 4-point, the equation for the 4-point diagrams, and so the 2-point diagrams, they will be self-consistent, sort of Schwinger-Dyson, simplified Schwinger-Dyson coupled equations. And then we have to fix the parameters that are the quark masses and coupling constant by fitting some meson masses that are not also, some of the meson masses will be already predicted by the model. So this is the relation when you take into account that mesons are generated in the adjoint representation and quarks are defined in the fundamental representation. So they are not identical. These coupling constants for each of these two different words are different. And you see here the up-up quark, I mean the up-up anti-up interaction depends on the G00 that's generated by the lambda zeros, the generator of this singlet part, and by also G88. So it will depend on the strange quark mass in the U3 flavor group. And then with this, we see the emergence of a symmetry breaking in the C quarks in this one loop level. And then also there will appear, they are not written here, different flavors will depend, will have mixing terms, mixing interactions, and different mesons will also have mixings if you take here the diagonal generators of the group, and this will depend on the mass difference between the flavors. This is the bit-salpeter equation at the Born level for constant. These are not yet momentum-dependent interactions. They are constant interactions, but they are flavor-dependent. So each meson has a ij specific one. So for the pion structure, the charged one, you have J11 and J22. For the neutron pion, we will have G33. And then for the kaons, for the eta, and for the eta prime, the same way. So the issue is that when you calculate, this is the polarization tensor. When we calculate this polarization tensor, we have to take this trace in the flavor space. So we have here the generators in the adjoint representation, but we have here the quark propagators that are also matrices, 3 by 3 matrices. And then if we neglect this matricial structure of these propagators, these mixings will not appear. So this is the idea here, is to write the quark propagator in the adjoint representation. So this S0, S3, and S8, they depend on the quark mass differences. And then we have structures for different structures that will contribute in the polarization tensor. Basically, they depend on the generators 0, 3, and 8 of the U3 group, and then mixings of the, here, mixing terms of the up, down, up strange, and down strange will give rise to pion, neutral pion, eta, eta prime. So this is a sort of a usual table that I take for doing numerical calculations. This is a fit for the current quark masses that are close to the PGG values, although it's an effective model, this is not necessary. And then an ultraviolet cutoff, and then the resulting quark effective mass. And then I will not show a lot of results concerning the spectra, but I will just explore here the fact that if we are calculating the spectra, I just emphasize that here we have the anti-up quark. This interaction depends on the strange quark mass. And then we can take the strange quark mass and vary for a wide range of values. So these are plots of the up and anti-up interaction, constituent up quark mass, and the difference between down and up constituent quark mass as a function of the constituent strange quark mass. So it varies from a long range, nearly 0 to, let me say, almost infinite, it's above 1 GeV. And this is a normalization point. That means all the interactions are flavor independent. Corresponds to the three-level Nabu-Lavoisier model. We see that the variation is of the order of 10% or 20%. And this shows a sort of stringent content of the up and down masses and properties. Here is the quark mass difference as a function of up and down, as a function of the strange quark mass. So all the up and down sector are calculated self-consistently. Only the quark effect, the strange quark mass is varied randomly. This is the variation of the neutron pion mass as a function of the strange quark constituent mass. For different, there are here 3 sets of parameters with 2 ways of considering one of the coupling constants. This is not important. I mean, the important is that all of them shows the presence of the C strange quark in the up and down quarks. And here is the difference of the charged pion mass with the neutron pion mass as a function of the strange constituent quark mass for different sets of parameters. And note that this difference is I forgot to put the reference, but it's known that this mass difference, most of it is of electromagnetic origin. Just 0.1 MeV comes from strong interaction. So this is precisely of the same order of magnitude, should be to reach here 0.1 MeV, right? So it's very good fit. and varies a little bit with the strange quark mass. This is the variation of the weak charged pion decay constant that was fitted to a little bit higher than the experimental value, 100 MeV here. In the physical point, that's a little bit above this normalization point, and the variation is quite high, 10% of variation for a large range of strange mass. So this I did with a previous student. This was in the beginning was not to be for real, but the results show some nice results. The results were quite interesting. So we took the U5 non-Boolean model with charm and bottom, and we used the same procedure that are present in several calculations using vector interactions, punctual structureless interactions with a cutoff, ultraviolet cutoff, but we changed, besides introducing the flavor-dependent coupling constant, we also choose a different way of regularizing the model. By means of a non-covariant ultraviolet model, it means that only the 3 momenta will undergo a cutoff. And it turns out in the results that the best fit we have for some meson masses, as we must do in the model, all these cutoffs for the 3 momenta are nearly the same, around 400 to 500 MeV. And then with this, we kind of have an uniform interpretation for the ultraviolet cutoff, because it's strange to take a cutoff for very heavy quarks, that you take the bottom almost 5 GeV mass, which is the cutoff that could be, I mean, the physical meaning of a cutoff that usually is clear for a low energy model may be a little bit confusing. And then also, this is for heavy quarks, but for the light quarks, it doesn't really matter if you take non-covariant or covariant regularization scheme. The results are very similar. So we have 5 parameters, 4 quark masses, because you take up and down quark masses generated, and then the strange and the charm in the bottom, 5 parameters plus a coupling constant or a cutoff. And then we describe, if you take the full multiplet of pseudoscalar mesons in the U5, you would have 25 mesons. But since up and down are degenerated, all the charged and neutron mesons become degenerated also. So we can count 7 pseudoscalar mesons or 21. That's the same analysis. And then we also give a look in the scalar multiplet. And then we find results. I will not show everything. We find results for the pseudoscalar that are good inside 6%, and for the almost all the scalar mesons within 10%. So let me show the results. We have 2 sets of parameters, 2 and 3, the experimental value of these masses. These are 7 masses. 5 of them were taken to fit, and the other 2 are already predictions of the calculation. Here there are several types of calculations with the standard non-Boolean but the non-covariant cutoff, the flavor-dependent coupling constant, but neglecting mixed interactions, and also in the limit where we neglect the heavy quark condensates. They are strongly suppressed because their current masses are large, so they are strongly suppressed. We did this sort of exercise to switch them off to see what happens. And for the light mesons, this makes almost no difference, pion, kaon, and also for the charmed one. But for the heavier one, mainly for the heavier one, they have an interesting effect to show that results with these condensates overestimates the resulting masses. So maybe the model has a problem to overestimate the heavy quark condensates. And then this is the structure of the polarization tensor if you consider all the terms with those mixing terms that appear by considering everything in the adjoint representation. So if you see, this is the 8, generator 8, the 15, and then 24 and 0. They have mixing terms that are very strong, very strong. They have large contributions, numerically speaking. So we also counted the effect of the renormalization of the, because of due to the C quark on the constituent quarks. So we find also that for heavier mesons, the effect is still stronger than for the light mesons. So these are the generators that give rise to eta prime, and also to the so-called eta C and eta B. They have been measured, but they are less known than the lighter eta prime. So here we also have different types of calculations, but note that the mass of the eta prime with those mixings, they are quite close, within some few percent, to the experimental value, and of the eta also, it's very close to the experimental value. The eta C and eta B, they are a little bit overestimated, their masses, though, so in principle, this could be attributed to the overestimation of the heavy quark condensates. And there is another thing that's curious, but we don't expect this to be really realistic, to interpreting the sigma F0 500 and F0 980 as quark anti-quark. They have sort of values that are improved, but we cannot say these results mean a lot of things, because there are many calculations indicating they should have other components like tetraquarks, glue balls, and so on. In any case, their values are considerably closer to experimental value for these scalar mesons. So also, by varying the same way I varied the strange quark constituent mass, we also varied here the charm and bottom constituent quark masses to understand the effect on the meson properties. These are the up quark mass variation with respect to a heavy one. This H may be C or B, depending on the color here, or a mixed combination of the variation of the two, that's the empty ball. So the variation here is quite large for the up, and for the strange, this is no, it's not large, it's 1%, around 1% of variation for a very large range of heavy quark masses. Here, the pion mass as a function of the heavy quark constituent mass, this is very large. This is 20% of the value of the pion mass. For the kaon, this variation is much less, of the order of 1 or 2%. This is certainly overestimated. This contribution for the pion mass certainly overestimated. This is the variation of the pion weak decay constant, is less than 1%. This agrees with other expectations, and this is the variation of the kaon decay constant with the heavy quark mass. So the issue is that the problem with the pion here is that the mass of the up quark with respect to the variation of the up quark with respect to the mass of the up quark is much larger than the variation of the strange quark mass. This gives a different behavior of these two curves, the opposite behavior. So we can try to understand a little bit more these mixings by taking parameterizations of the mixings that have been done for the pseudoscalar mesons. So here we can write, I'll take this last line, where you can write the pion wave function or state as a function of the up and down composition and the contribution of the other states, in particular here, the eta, that the state of gives rise to the eta particle. That's besides the mixing between eta prime, the neutron pion also has mixings with eta prime. The eta pi 0 is the leading one. Then I will neglect the mixing with the eta prime. And then we find that the state or the wave function or the state of the neutron pion depends differently on the up and down states. They are corrected differently because of the mixing, but also on the strange component. And then by doing a simple calculation here with the parameters that were used along this with the Nambu-Ion-Lalazinho, we find that the contribution of this state for the pion mass is of the order of 1 to 5 MeV. That's the same order of magnitude the curves have shown. And there are other estimates. It's difficult to assess what is a contribution of the strangeness on the pion mass. Anyway, there are some, maybe by means of, there are some ideas maybe. And then the same thing we are doing or start doing for these heavy quark contributions for the pion and kaon. And then we have also that those mixings from the polarization tensor lead to a charm and bottom contribution for the pion that are proportional to these mixing interactions. So maybe there's a way of detecting neutron pion from this transition of eta B and eta C that should be proportional to, these are teeny effects, so it's not, I don't know how would be this sort of contribution experimentally. So we can, if you take eta C or eta B at rest, we have a still good estimate for the kinetic energy of the neutron pions that should be taken. So just show this slide. I also calculated the strangeness, this sort of strangeness content of the C cloud to the scalar quark-antiquark state that should be attributed to the light scalars. And then we have a strong variation that leads also to a change of a hierarchy if we take the A0 and kappa, 800 and 980. They have all models, most of models predict an inverted hierarchy. And then the variation of the strange quark, constituent quark mass may correct this wrong hierarchy in the spectra. Also, I could calculate the ratio of the mixings of A0 and F0. They have basically the same masses, and they have a mixing measured in BESS3. This is the ratio that was measured experimentally. The experimental analysis provides two different values, and these different values go along with the calculation by taking into account this strange content in the C of the Nambu-Ion-Lalazinho model, in the C quarks level of the Nambu-Ion-Lalazinho model. So just to show, and then it looks like that when you consider these mixing terms of the polarization tensor, if you want to add one quark and one anti-quark, what you get is not really a very definite, I mean, they are not really exactly a flavor eigenstate as you have here for isolated quark anti-quark. So this is a summary. So I try to show a mechanism in which vector mesons may probe the axial current, and then some effects of mixings due to the flavor symmetry breaking in the C quark level, and they help to probe the strangeness, bottom and charm content of light mesons. So there are some works ongoing that are planned also, and thank you for your attention.
Thank you, Fabio. Okay, now open questions or comments, please.
Fabio, very interesting, this mixing of the quartz. I have 2 points. One, is if you have thought about the implications of the mixing of the quarks to the CKM, or because you have
Yeah.
channels that,
No,
yeah, things like
I
that.
didn't. Yeah,
Okay.
because in this level here, this sort of
Yeah.
of matrix is parameterized by taking into account the CKM matrix.
As
so
well.
These
Ah,
parameters
okay.
that appear here, this theta,
Yeah.
and here, epsilon 1 and 2, they have some grounds in the CKM.
Yeah.
But here, this takes into account more effects because this is already in the consistent quark level, in the dressed
Yeah,
quark
because
level.
this could imply in consequences in the CP violation.
Okay.
Because when you have some transitions,
Yeah.
sometimes the angle for CP violation is very small in one channel, in the other could be large.
Oh, okay.
Yeah, so this could be interesting.
So you
this
mean-
is one observation.
All right.
And the other observation is about for example, the pi naught decay in two gammas.
Right.
You have
Yeah.
2%, but this is very precise. I don't know if this could put some boundaries
No, but
on
you
this
mean-
mixing between the quarks.
No, this is you mean the pion decay constant. This is
No,
No.
pi naught.
Yeah,
the
pi naught.
axial anomaly.
Yeah, sure.
that
I
we had.
didn't calculate that.
Okay.
I should calculate this
Okay,
diagram
very
with this
good.
flavor. Yeah, sure.
Okay.
More questions or comments? Yeah, Fernando.
Nice work. Did you compute the charm quark condensate?
Yes.
I saw there.
Yeah, it is.
How much is that?
I didn't put here the numerical values. They are not large. They are not large. The C and B quark condensates, they are relatively smaller than the strange quark condensate. They are of the order of, at most, I guess, 10% or 20% of the current quark mass. So they are relatively much smaller, but even that, they give a large contribution here for the heavy. If you take these values in this bracket here, this is the value with 0 condensates. And these are the values with condensates. So the value is reduced by more than 10% because you switch off the heavy meson condensates. So they have but I didn't write the value of the condensates themselves here.
Also, at the beginning, you mentioned this 1% of the charm content in the proton, in the nucleon, and coated Brodsky and collaborators. What is the connection what could you say about that? So you mentioned at the beginning, and maybe I missed this during the talk, but what is your statement about that?
Well, in that paper they proposed, they took a different type of mixing. You take proton UUD, and they included UUD CC bar. So this is the mixing they take. Two scalars, the same quantum number of the proton, but one includes CC bar. So this is a kind of different mixing, right? This mixing does not depend on the representation of the flavor group. So these are states with the same quantum number, so they may add to each other. But the result is that almost many things we did here, the resulting contribution for example, the pion decay constant is at most of the order of 1%. If you take the up and down quark mass, the strange quark mass is at most of the order of 1% this contribution of the half quark. So we have basically the same order of magnitude, but we don't have a nucleon altogether. We have just a constituent quark, and with a different mechanism. That's not the same mechanism.
Okay, so I see that you established a connection between the charm condensate and the fork component of the proton in the language of Brodsky, which contains charm, right?
Yeah.
Okay, that's interesting. That's new.
Okay.
Usually people do not associate these two things. So usually people just say that the charm condensate is 0 and this fork component has some different origin.
Yeah, many people argue that this should be 0, the CC bar condensate, but there are several calculations showing that it could be non-zero. Yeah, sure.
Nice work. So can you say anything about exotic states like tetraquarks, pentaquarks?
Yeah, I mean, I didn't calculate any of them, but of course, this sort of mixing will certainly show up. This sort of mixing certainly will appear. And I don't know, they are expected. I mean, maybe if you include mixing with exotic states, I don't know if you refer to that, but maybe you were saying something I didn't get. But I mean, there's no problem in including other states, in particular for the scalar mesons that are quite problematic. But and this kind of mixing should appear in the same way.
Thank you.
Thank you. More questions or comments, please?
Thank you for the very nice talk. Just a curiosity, can you comment on the symmetry breaking effects on the couplings?
Yeah, you mean? Well, this difference between these coupling constants in the different channels, they appear because of the flavor symmetry breaking in the Lagrangian, right? So they are not exactly proportional to this quark mass difference, but this quark mass difference are very important here. And then besides that, the meson interactions, the interaction that define the mesons, they are very different from the interactions that define the quarks. And then I don't know if that's the point. I mean, you have both types of contributions of this flavor symmetry, right? I didn't say explicitly, but here we have two sorts of mixings take into account different channels for each of the quark flavor, and also we can have different sort of mixing interaction that's directly proportional to the quark mass difference.
More questions or comments to Fabio? If not, I can say thank you again, Fabio, and all speakers today. And today is Friday. I hope you enjoy São Paulo by night. But careful.